Okay. All right, thank you. Okay, we're going to talk about dynamics and kinematics. Some examples like gyroscope, joints of robots, and supported, a radio telescope. For example, if there's a satellite that wants to align the antenna with a dish on the ground, it has to do some rotations, maybe 1 or 2 or 3 rotations until it aligns it. Right. Kinematics and vibration. Right. Tomorrow would be dynamics. Okay.
So you will be required right now for kinematics.
Yeah, that's the only thing we're going to do now. Yeah.
Tomorrow will be
Dynamics.
both civil and also it's a bit much and a bit different.
Okay. Okay. All right. So the fundamental relations developed for the plane motion. Plane motion means if we're talking about x, y, z, then we're talking about only x and y. Our rigid bodies may also be applied to the general motion of three-dimensional bodies. So summation of all the forces applied to a rigid body, and rigid body is a collection of many particles, for example, that has a point of G, and that point G is the center of mass of this rigid body. All the forces applied to this rigid body, the summation of all the forces, would be equal to MA. F equals MA. And on the left-hand side is the forces, and the right-hand side is related to kinematics, which is angular momentum, h of g, h about point g. So a rate of change of angular momentum, which is h dot, is torque. So summation of torques equals h dot about point g. Angular momentum in 3D, h equals summation of all the, if we assume that pi is our particle, and we have many particles from 1 to n, the position vector of the particle is denoted by r, vector r, from G to P. That's the position vector. And since this is a rotational body, so you're going to have some angular velocity, omega. And velocity is always tangent to the path. So if you assume that at the point P1, Pi, we have a velocity that would be v prime of I for that particular particle, then velocity would be omega cross r. And note that all the three axes, x, y, and z, each one has a angular velocity. So angular velocity components would be omega 1, or omega of x around x-axis, omega y around y-axis, and omega of z around z-axis. And the total or resultant angular velocity of the rigid body would be the omega, vector omega, that we see here.
What is the x sub
and Z. Okay, IJK. Well, oh, those are IJK. There's a mistake here. Yeah, this is. Yeah, that's J and K. I apologize. Yeah, so this is J and this is K. Yeah. Oh, you're welcome. So that would be the cross product that we do. Then the x component of angular momentum, h of x. If we just put the components, we assume that we have omega x, omega y, and omega z. These are the components of angular velocity of the frame, x, y, z, and x of I, x of j, and x of k. That would be the position vector in that frame. Then our x component of angular momentum, which is h of x, would be calculated through this substitution. And finally, h of x would be equal to I of xx, I bar of xx. When we have bar, means about point G, about center of mass. So x of, I of xx means moment of inertia with respect to x-axis times angular velocity of x-axis minus moment of inertia of xy, again bar, with respect to g, minus I of z xz times omega of z. So this is h of x, and this is h of y, and h of z. Okay, so this is just some derivations that we're going to use later. Now, moment of inertia. Transformation of angular velocity omega into h of g, angular momentum with respect to point G, is characterized by the inertial tensor for the body, which is this matrix. Okay, now this matrix, if the body, the mass of the body is evenly distributed about the axis of rotation, then so these three components and these three, I'm sorry, apologize, these three. So the upper triangle and lower triangle become zero. They vanish. This is only if the body is rotating about an axis and the mass is distributed evenly. Okay, so in that case, all you have in your moment of inertia matrix is I of x, I of y, and I of z. The rest would be zero. No, you cannot. Exactly. If it's not unbalanced, then no, you cannot. So when it's distributed evenly, then those three terms vanish, and then you're going to have this matrix. So with respect to the principal axis of rotation, axis of inertia, you're going to have this matrix. Okay. The angular momentum h of g of rigid body and its angular velocity omega have the same direction. Only and only if our angular velocity is directed along a principal axis of inertia. In other words, if your angular momentum is aligned with your angular velocity vector, then we have h is parallel to omega. So let's take a look at, let me show you one. Okay, take a look at this image, this figure. The disk is tilted, right? This disk is tilted. It's rotating. It has some angular velocity, right? So now, if I say what's the angular velocity is right here, right? This is our angular velocity. So your angular velocity vector would be there, but angular momentum would be here. They're not aligned, right? So if they're not aligned, back to the same slide we had. So the angular momentum h of g of a rigid body and its angular velocity omega have the same direction if and only if omega is directed along the principal axis of inertia. Okay. Any question? All right. Okay. The momenta of the particles of rigid body can be reduced to linear momentum. L equals mv, and angular momentum about g is it has the three components that we just saw in previous page. So just as a summary on this page. Rigid body angular momentum in 3 dimensions. The angular momentum of a body constrained to rotate about a fixed point may be calculated from this equation, which is angular momentum about point O. Okay, point O on this frame. Angular momentum about point O equals R cross, R is position vector of the particle, P, cross mv plus hg, which means center of mass of this particle, whatever it is. If that's g, so angular momentum of that part plus R cross mv related to the particle, 3 components. Or the angular momentum may be computed directly from the moments and products of inertia with respect to the O, X, Y, Z frame, which is this frame. Okay?